So if you want to read along a little bit here on page 232, I'm not going to go through the whole stuff here in the book, really. They talk about dynamics, they talk about statics, they talk about static equilibrium, they talk about dynamic equilibrium, okay? In 7.2, statics is the physics of keeping objects still by applying forces to them. Static equilibrium, an object state of motion when all the forces acting on it are balanced, and it's not moving, I guess one could say. Dynamic equilibrium is when it's moving at a constant velocity. And obviously you want your bridges to be in static equilibrium. Center of mass is something that is talked about a little bit at the university level. We don't worry too much about it, but just sort of a brief introduction. Is the single point at which the entire mass of a body can be considered to be concentrated. Okay, it's like the center of gravity. And if you look at 7.15, the bottom right-hand corner there's a picture of Wile E. Coyote standing underneath the big rock, and of course we all know what's going to happen there. When the center of gravity is not above the balance point, well then it's going to collapse. Okay, you probably won't hit it. By the time you get back, I'm going to be done. Okay, so if you flip to page 234, balancing forces again. Forces tend to cause translation and rotation depending on where they act with respect to the center of mass. How does this tendency relate to statics, the study of no motion? An object can be in a state of translational static equilibrium only under two circumstances: when there's no force applied to it, or when the force applied to it acting through the center of mass all balance one another out. In other words, the net force is zero. Okay? So really what I want to get to is these examples that are here. Not the ducks, no. This guy's got, the author's got something about ducks. Figure 778 illustrates a typical case of static equilibrium. Several children are playing a parachute game during a phys ed class. So you probably played with a parachute in phys ed class, right? What force must child 8 apply if all the children in the circle are applying the same 35 Newton force outward in order to keep the parachute in translational static equilibrium? So there's the picture. Okay, 7.7b, and we've got 35 newtons there, 35 newtons there, 35 newtons there, 35 newtons there, and 35 newtons there. Well, they got figure 8, but all the other ones, right? Well, if they were all applying 35 newtons, what would child number 8 need to do? Well, obviously it's going to have to be 35 newtons, right? The net force has to be 0. This 35 and this 35 will cancel. That one and that one will cancel. That one and that one will cancel. So clearly that one and that one have to cancel as well. So child number 8 has to have come up with 35 newtons. And then therefore the net force is 0, which means it has a net acceleration of 0. If it's already at rest, it will simply stay at rest. And example number 2, part B says, what extra force would child 4 and 6 each need to apply if their teacher was playing this game in position 1 and applied a force twice that of a typical child? So in other words, we've got 35 there, 35 there, 35 there, 35 there. This guy would be 35, right? What values would these have to be if the teacher's pulling with 70? Would it be 35? 45? How'd you come up with 45? Oh, just says
Well, that's a degree.
Well, do we need to worry about those two?
No.
All right, so what are these values going to have to be? We got 35 and 35 here. Now, what happens with the 70 and this 35? Well, we get a net force of 35 this way that we're going to have to balance, right? We also have to balance out this one here as well. Okay, so let's just have a look at this here. If I were you, I would sort of draw that out so we know what's going on. Yeah, I would. So the question is, we've got these kids, everyone's pulling with 35, and then the big bully teacher comes in and decides to pull with 70, right? And so the question is, what do these two kids, what extra do they need to pull? I'm going to label this one F4, and I'm going to label this one F6, as they indicate in the book. Okay? So in other words, the X components of F4 plus F6 need to balance an additional 35 newtons. Okay, they were already pulling with enough to balance 35, and then the big bully teacher started pulling with more. So they need to come up with an additional 35 newtons of horizontal force between the two of them. Okay, so in other words, F4x plus F6x have to be equal to 35, the additional force. Okay. Now, if I just go into this triangle right here, and if that's F4, that's my component down there. It's adjacent, so this is going to be F4 cos. Now, do we know it's 45 degrees?
Yeah.
Does it say anywhere in there?
It equals 45.
Okay. So F cos 45, F4 cos 45 plus F6 cos 45 have to be equal to 35. And we know that F4 and F6 are equal forces. In other words, I can ignore the fact that there's F4 and F6, just call it F because they're the same, right? So I'm going to say like F cos 45 plus another F cos 45, or in other words, 2 F cos 45, 35 newtons. So F is simply going to be 35 divided by 2, and take the inverse cos of that. No, I'm wrong about that. I am wrong about that. It's going to be, let's write it this way. Let's write 35 over 2, which of course is 17.5, and then F is going to be 17.5 divided by cos 45. Yeah, that's right. 24.7 newtons, and this is extra. Extra. So another quick look at this here. So the question is, how much additional force does kid 4 and kid 6 need to pull? The x components, the sideways components, need to balance an additional 35 newtons. So the x component of 4 plus the x component of 6 have to equal 35, the additional. Because of the way this is set up, that's my F4, my Fx is cosine, so it's F4 is cosine 45, is my F4x. Same thing with the 6. Because F4 and F6 are equal to each other, I'm just going to say 2 times the force times cos 45 is equal to 35. And then I solve for 24.7 newtons extra, which means, right, already pulling with 35 newtons. So it would be 24.7 plus 35, which of course is 59.7 newtons each would have to be pulling to balance the teacher. What could they do to their angle to make it easier and pull less? What could they do to their angle so they wouldn't have to pull as much? Make that angle less, right? You're right there, right? If they made their angle like this, right, then it wouldn't be as hard. Sure, yeah, sure. Yeah. Yeah. I would recommend you guys spend the rest of the period working on the handing. If you get it to me, I'll try to mark it tonight, and then you'll have it back tomorrow. Thank you, Justin. That's a very good idea. Yeah, you can do that. There are some textbook questions that you should really look at. Okay, I'm just going to give you that list. You really need to do number 4 on that list. Okay, I'm going to go through number 4 tomorrow. Okay, 237, 1 to 4. Do number 4, or at least have a look at it. I'm going to do that one tomorrow. Yeah, or I've got a couple here. Okay, and yeah, try to get that hand in today.